Hello everyone. Welcome to the third and final installment of our review of the cardiovascular anatomy and physiology. In this lesson, we're going to get into some of the more complicated physiological concepts. I'd venture to say that this is probably one of the more difficult topics in the entire EMT program. But don't worry, I'm sure you'll be able to master it. Okay, let's start with a real quick review of circulatory physiology. The heart's job is to pump blood through a complex circuit of blood vessels to all areas of the body. Now, the heart is actually two pumps in one. The first pump is located on the right side, and its job is to send blood to the pulmonary circuit. Here, it can pick up oxygen and drop off carbon dioxide. The second pump is on the left side. It pumps blood to the rest of the body. We call this the systemic circuit. Now let's talk a little about blood pressure. When the ventricle contracts, blood is forced into the large arteries leaving the heart. That force exerts pressure on the walls of the arteries, causing them to bulge. This pressure is greatest close to the heart and weakest at the very end of the extremities. We can actually feel the pulsation created by this pressure where arteries lie close to the skin. We call that a pulse. Now, we use two terms to describe pulse locations. Those close to the core of the body are called central pulses, and those further out in the extremities are referred to as peripheral pulses. Now, it turns out we can actually measure the pressure in some arteries. This is the vital sign we call blood pressure. You'll learn later in the course how to actually measure a patient's blood pressure. At this stage, I simply want you to have a basic understanding of what you are evaluating. Now, there are two different values we obtain when we take a blood pressure. The first is called systolic pressure. The term systole refers to contraction of the ventricles. This is when the pressure in the arterial walls is the greatest. When we measure this value, it's called the systolic blood pressure, and that's the top number you see recorded in a blood pressure. Now, even when the ventricles are not contracting, the period called diastole, there is pressure on the arterial walls. We measure that value. It's called diastolic pressure, and that's the bottom number. Now, obviously, the strength of the heart's contraction will affect BP or blood pressure, but there are other factors at work here. Let's look at those. First, understand that blood pressure requirements change depending upon many factors. For example, when at rest and our body's needs are reduced, we can get by with less pressure than when we're exerting ourselves doing heavy physical labor. Emotions and stress also have a significant effect on blood pressure. You may recall in part 2 that our arteries contain muscles that can change the diameter of the blood vessels. Altering the size of the blood vessels changes what is known as vascular resistance. I'll use these illustrations to explain that concept. When we constrict a blood vessel, this results in an increase in vascular resistance. This increase in resistance corresponds to an increase in pressure in that vessel. The opposite is also true. If we dilate a vessel, the resistance goes down, as does the pressure. So as you can see, blood pressure varies depending upon how forcefully the heart beats and whether the arteries are dilated or constricted. But as they say in the commercials, that's not all. There's also another variable called hydrostatic pressure. Now, hydrostatic pressure is simply the force applied to the blood vessel. If the BP gets too high, it can actually force fluid to leak out. This is especially possible in the smallest vessels, the capillaries. This loss of fluid can cause all kinds of problems. Things like edema or swelling, up to and including an actual loss of circulating volume. All right, so now hopefully you understand the dynamics of how the heart pumps blood and how it affects the pressures within the system. Well, the reason we cover this information is so that you can understand the concept of perfusion. Perfusion is defined as the movement of blood through tissues. For cells that make up our different organs to survive, they must have an adequate blood supply, or as we call it in the healthcare profession, they need adequate perfusion. Well, what does this perfusion do for us? Well, it's all about transportation. When perfusion is good, the cells receive the necessary oxygen and nutrients they need to do their job. Remember though, this blood flow is also important for transporting the CO2 and the waste away so that they can be eliminated. Now there are a couple of other terms I need you to understand. The first is aerobic metabolism. Aerobic refers to oxygen. And when perfusion is good, the cells receive enough oxygen to carry on their metabolic activities necessary for health. So aerobic metabolism is the normal state. Now, if for some reason perfusion falls, the cells suddenly find themselves short on oxygen. They have the capacity to change to another form of metabolism that does not require oxygen. It's called anaerobic metabolism. Unfortunately, this only works for a short time. So if the problem isn't resolved pretty quickly, the cells will start to die due to this absence of oxygen. We have a name for the condition in which perfusion falls. It's called shock. All right, how are you guys doing so far? Let me do a little recap. Our heart pumps blood to all of the body's tissues to deliver the stuff the cells need to work. The delivery of blood is called perfusion. The perfusion needs change occasionally, and our body can compensate by raising BP. The heart beats more forcefully, and the blood vessels constrict to increase pressure and delivery. When perfusion needs fall, the opposite will occur in the heart and the blood vessels. The perfusion delivers stuff the cells need and removes the stuff they don't need. If perfusion gets too low, the cells can temporarily swap over to anaerobic metabolism to buy some time. However, if the problem isn't fixed pretty soon, bad stuff happens, and we call this shock. All right, moving on. Now I want to tell you a little about how those gases, oxygen and carbon dioxide, are carried in the blood. I'm going to use these illustrations to help me explain that. On the left here we're going to discuss oxygen, and on the right we'll do carbon dioxide. Let's do oxygen first. When oxygen leaves the lungs, here let me draw some lungs. It enters the bloodstream. Now 97% of that oxygen is going to hook up to a red blood cell. Specifically, there is an iron-containing protein called hemoglobin that loves to bind with oxygen. Now the remaining 3% kind of gets to the party a little late, and all the hemoglobin is loaded. Well, this small amount of oxygen, it just drifts along dissolved in the fluid. So in summary, 97% of oxygen is transported on hemoglobin. 3% is said to be transported in solution. Okay, so what's the big deal of this? Well, I'm glad you asked. You see, only so much oxygen can be transported in solution. Without the red blood cells and hemoglobin, our blood cannot deliver enough oxygen to the cells. So any condition that decreases hemoglobin, things like decreased blood volume, decreased red blood cell counts, or even iron shortages, can dramatically affect the oxygen delivery. All right, now that's oxygen. Now let's look over here on the right and talk about CO2. Carbon dioxide comes from the cells. It's created in the chemical reactions that occur inside the cell. Here, I'll draw a cell here. See how the CO2 leaves the cell and enters the bloodstream? Well, something a little different happens with this gas. Hemoglobin is okay with CO2, but it'll only hook up if there's no oxygen around. About 23% of the CO2 will bind with hemoglobin. Now another 7% will just dissolve in solution, kind of like that oxygen we talked about earlier. But what happens to that other 70%? Well, it's changed and transported as a substance called bicarb. Now I'm going to switch slides to show you how that happens. All right, don't freak out. This is chemistry, but we're going to keep it really simple. Just follow along. We're going to move from left to right. The carbon dioxide chemically reacts with the water in the blood to form a substance called carbonic acid. CO2 plus H2O yields H2CO3, which is the carbonic acid. Now, as acids go, carbonic acid is kind of a wimp, and it quickly breaks down into hydrogen, the H here, and HCO3. Well, HCO3 is bicarb. So that's what they mean when they say it's transported as bicarb. It's just another way of saying that most of the CO2 that enters the blood undergoes this chemical reaction. So right about now you're thinking, what the heck do I need to know this for? Well, here's why. See this carbonic acid? It may be a wimp, but it's still acid. And too much acid is bad. As a matter of fact, it can kill you. So, we worry when a patient either builds up too much carbon dioxide or can't get rid of what they have in their blood. Because high carbon dioxide equals high acid levels, and that can lead to organ dysfunction, which can lead to death if not promptly treated. Okay, let's wrap this lesson up. When the perfusion to cells falls, two big problems happen in relation to these gases. The first is hypoxia. That means there's too little oxygen reaching the cells. So they swap over to anaerobic metabolism, but they can't survive very long on that. Now the second thing that's happening is hypercapnia. Some books call this hypercarbia. Either way, it means there's too much CO2, and that leads to acidosis, and that's bad. Now the biggest problem of all is that these two bad things often occur together when our cardiovascular system is unable to meet the body's needs. Not enough oxygen, or too much carbon dioxide. Either will kill you, but if you get both, it kills you even quicker. All right, that's enough for now. I promise this will all make more sense as you go through the class and you learn about the various injuries and illnesses. All of these things are going to come back to those concepts where we fail to deliver oxygen to the cells or we fail to remove the waste products that build up. It might help to watch this video again if you missed a little something. You can also discuss these concepts with your instructor or drop me a message if you have a question. Later.